So hopefully you watched the intro to related rates video like I asked you to, so you have kind of an idea of where we're going in this section. We're talking about applications here. If we're pumping air into a balloon, the radius is getting bigger, the volume's getting bigger, the surface area is getting bigger. So a lot of things are changing, and they all change in relationship with one another. We can use the chain rule and implicit differentiation to solve these problems. So let's look at just a very simple introductory example. A is the area of a square whose sides are length x, and their length varies with time. So we're going to start our process that we will use to solve these problems over and over again, the first step of which is to just draw a picture. And luckily squares are not that hard to draw. We're going to pretend like it looks like a square. And I always label things, so this side is x, that side is x. All the sides are x because it's a square, so all the sides are exactly the same. Write an equation that relates a and x. Area is x squared. Find the derivative of your equation with respect to time. It gives you an equation that relates the derivative of area with the derivative of the length of a side. So, chain rule and implicit differentiation at work here. The derivative of a with respect to time is equal to 2x times the derivative of x with respect to time. At a certain instance, the sides are 3 feet long, increasing at a rate of 2 feet per minute. How fast is the area increasing at that instant? So I usually like to think about what I know and what I need. What I need is how fast the area is increasing. How fast something is happening is a rate. A rate is a derivative. So this is the tricky math way of saying what is dA dt, and it's asking the question when x is 3 feet long and it's increasing at a rate of 2 feet per minute. So we're given x and we're given dx dt, so we can just plug and chug and figure out dA dt is 2 times 3 feet. I'm going to keep my units in here because it keeps me straight. 3 feet times 2 feet per minute, and we end up with 2 times 3 times 2, 12 square feet per minute. Perfect. Easy example. This week we're going to do some simple examples. Next week we'll be doing some more complicated examples. So this week we will focus on geometric examples and Pythagorean theorem examples. X squared plus y squared equals z squared, which is what intro problem number 1 is. We have a 15-foot ladder resting against a wall. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. So here's my wall. Here's my ladder. I'm going to label the ladder 15 feet because the ladder's not going to change. Now, how far the ladder is from the building is going to change, and how far the top of the ladder is from the ground is going to change. I like horizontal stuff to be X's and vertical stuff to be Y's. You could call them D and H for height and distance. You could call them Charlie and George. You can call them whatever you want to. I like X and Y because I'm boring. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. So I see a rate. It says that being pushed towards the wall, that means it's going this way. So X is getting smaller. dx dt is minus 1/4 foot per second. And initially we're 10 feet away. How fast is the top of the ladder moving up the wall? So I know this. I need dy dt, how fast the top of the ladder is moving up the wall. And I want to know that when t is equal to 12 seconds after we start pushing. So I need a relationship between x, y, and 15, and that's thanks to my old pal Pythagoras, because he tells me that x squared plus y squared is equal to 15 squared. Love that Pythagorean theorem. Now we are going to differentiate the Pythagorean theorem. 2x dx dt plus 2y dy dt is equal to the derivative of 15 squared, which is not a big fat 0. Everything there has a 2 in it. We could divide by 2 and just have x dx dt plus y dy dt equals 0. And I'm going to copy that over to the next page. I'm also going to copy down my no dx dt is negative 1/4 of a foot per second. Now, my goal is to figure out what dy dt is. I need a x, I need a y. I know that initially the bottom is 10 feet from the wall, that x is a function of t. It's moving closer to the wall at a rate of 14 feet, 1/4 of a foot per second. So it's equal to 10 minus 1/4 of t. Makes sense. The derivative of this little equation here is negative 1/4, exactly what we needed. So I want to know what's happening after 12 seconds. X of 12 is equal to 10 minus 1/4 times 12. So 10 minus 3 is 7. I also know that x squared plus y squared is equal to 15 squared. So 7 squared plus y squared is equal to 15 squared. Let's see what 15 squared minus 7 squared is. 15 squared minus 7 squared. I get 176. Second square root, second answer. So y is 4 times the square root of 11. Because I want an exact answer, and often WebAssign will want an exact answer. So I'm going to leave it as 4 times the square root of 11, even though I don't know exactly what that number looks like. Now I can plug and chug. X is equal to 7. dy dx is minus 1/4. Y is equal to 4 times the square root of 11. dy dt is my goal that I want so very much, is equal to 0. Now it becomes a job for algebra. Divide both sides, I get 7 over 16 times the square root of 11, and this is going to be feet per second. Usually we finish up by writing down what we mean in the context of the problem, and when I do that, I usually go ahead and get myself a decimal answer that I can wrap my head around. So 7 divided by, open up a set of parentheses, 16 second square root of 11. So after 12 seconds, tell me when it happens. What's changing? Well, we were interested in how fast the top of the ladder is moving up the wall. The top of the ladder is moving up the wall at a rate of 0.13 feet per second. And there you can see the whole sentence. Same type of interpretation that you did on the last test. When did it happen? What's moving? What's changing? How is it changing? Don't forget the units. So that one used Pythagoras. Sometimes you are going to need to remember some of your geometry formulas. We did a square, now we're going to do a circle. The area of a circle increases at a rate of 1 centimeter squared per second. How fast is the radius changing when the radius is 2 centimeters? So even though it may seem silly, I'm drawing a circle. I'm labeling the radius, and the radius is changing. The area increases at a rate of 1 centimeter squared per second. So that is a derivative, dA dt. That's given to me. So I know it's true, it's not going to change. 1 square centimeter per second. I want to know how fast the radius is changing. So my need to know is dr dt. And I want to know how the radius is changing when the radius is 2 centimeters. So I've taken all these words and I have condensed them into know, need, and when. What do I know? What am I looking for? When. Know and when are the hard parts. When is something that is changing, and you're going to pick a specific instance in time. Know is not changing. So, area of a circle, pi r squared. So the derivative of area with respect to time is going to be 2 pi times the radius times the derivative of radius with respect to time. Well, this one's even simpler than the last problem because we have everything that we need just to plug right into that equation. 1 centimeter squared per second is equal to 2 pi times my radius, because I want to know dr dt when the radius is 2, and this is 2 centimeters if you're keeping up with your units, because now I'm going to divide both sides by 2 pi times 2. And remember, there's a centimeter that's coming over here, so when I divide centimeters squared by centimeters, I'm going to end up with 1 over 4 pi centimeters per second is dr dt. I'm going to write down this sentence. I'm not going to make you watch me. I'll pause. So like I did before, when I wrote my sentence, I went ahead and made it into a decimal answer because my brain has no idea what 1 over 4 pi centimeters looks like, but I have a better idea what about 8/10 of a centimeter